I'm going to present some recent work of ours on an experimental programming language called Sig-adlib, which is short for Signal Processing Ad libitum, or as you like it. And that's a curious little language with some dialectic properties. On the one hand, it's a managed language, runs on the Java virtual machine, but it's very careful on resources because you don't want to do garbage collection at real time. And then, most important for today's talk, it's a dynamic language, it's modular and extensible and still offers or promises high real-time performance. And it's mostly a functional language, but not quite. The data flow aspect is purely functional, and there are some procedural control flow aspects to it. And finally, the language was originally conceived as a compiler backend for yet another signal processing language, but it turns out that it's also nice to use directly and independently. For the kind of programs that we're dealing with, let's have a look at an example. This is just a bit of Java code that sums up elements of a stream of floating point numbers. And if you know nothing about numerics, you might want to do it this way, but actually it's a bad idea to just use a single variable and a single addition per loop cycle, because this has very bad numerical properties. The errors accumulate over time. And already in 1965, Kahan proposed this extended algorithm. I took the liberty of translating his original Fortran syntax into Java, but otherwise it's the original algorithm that takes care of the errors and makes the summation stable. That was a theoretical breakthrough in 65, but we don't really want to look at algorithms like this anymore. Well, C programmers still do, but we're not counting them, are we? And the big problem about this presentation of algorithms is, of course, referential transparency. There is none. If you look at a single variable S2 alone, it has 5 regions in the code where it means different things. And the original sin is to use variables often, and in particular, use them in a single iteration before and after the update. That makes reasoning very hard. It makes it very easy to break programs by arranging assignments in the wrong order. Obviously, there has been some work since 1965 in various areas. There are some graphical languages that focus on data flow networks. You have seen some data flow networks today already. Then there is algebra for the functional programming community. We have Mealy machines. We have arrows in functional reactive programming and many more things. And also object orientation can do some rather nice things using data abstraction to get things in a more orderly fashion. And the bottom line is the language that I'm talking about, Sig-adlib, has a bit of each of these 3 ideas. Actually, the way I would like to reason about the algorithm is using a data flow diagram like this. In the white box on top, there's the naive algorithm. You just have a delayed feedback and a single addition operation. And then there's 2 operations at the bottom that track the error that has been committed in each step and propagate it back into the next step for compensation. That's very nice to look at and to reason about. But unfortunately, graphical implementation languages suck very badly, so it's back to code again. This is just an example of how code could look like in a very modern functional reactive programming language called Rhine, embedded in Haskell. Don't mind the details. The important part is there is a big where statement, so all the variables are now just let binding, so they're referentially transparent by design. And then there is a magic Mealy combinator that takes care of the iteration. And there's another school of languages that has been very influential in the area, and that's the so-called French school of synchronous languages. This is an example in Lustre. The same algorithm takes care of referential transparency by explicitly marking variables of which the value before the update is to be used. And the synchronous languages come with another important idea because they are both declarative and very low level. They have very interesting ideas, and one is that there are 2 notions of time. There's macro time, that's the scale at which the clock ticks and elements of streams get processed, and then there is micro time, that's the time at which updates propagate through the data flow network. And usually synchronous languages come with a compiler that does a global static analysis to make sure that nothing goes wrong at micro time. And finally, there's the object-oriented world. Of course, in Java, since version 7 or 8 or something, we have streams, and the typical examples look like this. You have a data source, and then you apply some of the usual higher-order operations, like filter, map, and you end the whole thing with a fold operation to consume the stream. And then there is also some implicit parallelization if your data gets more biggish, but there's a problem. Well, with that approach, if you look at the implementation, all the data flow is actually routed through a single method, this one here, that's called try-advance, and that does two things at the same time. It observes one value of the stream, and it makes the transition to the next value. And by that design, streaming pipelines are forced to be linear. You cannot have an unzip operation. You cannot use a value twice. So something like the data flow network of the KN algorithm cannot be implemented. The Java designers of the Stream API don't try to read the details, are aware of this, and they suggest to use compensated summation in the implementation behind the scenes, but they cannot express the same algorithm in their streaming framework. And that's the place where Sig-adlib comes in as a signal processing language that can be used just like streams in Java, but that can deal with serious data flow networks. Sig-adlib is an embedded domain-specific language, so it doesn't have a syntax of its own, it doesn't have a compiler toolchain of its own. It just has some Java classes, so to create a program, you create a bunch of objects, and every object carries part of the interpreter to make the system work. So Sig-adlib ships as a pure library solution that runs on any JVM, doesn't require any special resources. And it has two APIs, one for metaprogramming for the construction of signal processing networks, and then another for execution. And the whole language is a bit aspect-oriented. The data flow and the control flow are described separately. The data flow API basically consists of interfaces where you can observe the value of a signal. So there is a signal source that encapsulates the actual producer of the value, and this is a side effect-free API. So by observing a signal, the stream does not transit to the next element, and that's how we can get around the Java stream linearity restriction. And of course, there are similar interfaces for the other Java data types, because we don't want to end up wrapping things in objects, because that would trigger the garbage collector. And on the program construction level, there are operations like map and zip and all the things. So if you have three signal sources, X, Y, and Z, then you can set up a data flow network that averages them at every point in time like this. On the other side, we have the control flow API that consists of a single interface called process that has two methods, one that you call to set up a computational network, and the other one called step that you call to perform one cycle of computation. Data flow networks are passive. They're not entitled to run or to terminate by themselves, but the step operation gets called by the outside as long as there is demand. And then, of course, you can reuse a component by calling init again, and then you can perform steps, and after each step, all the signal sources have updated values that you can observe. If you have ever written an Arduino program, you're familiar with this model. It's the same thing. And then at the meta-programming level, there are operations for control flow sequencing. This is like semicolon, P and then Q is a data flow network that at every step first triggers P and then triggers Q, sequenced in micro time. And R every 128 is a network that on every 128th cycle triggers R. And the catch is, because it's a dynamic language, we don't have global program analysis. The programmer must specify both the data flow network and a firing sequence that actually makes sense. That's the price that we pay. The usage pattern looks like this. First, you create some signal sources to observe, and you figure out the main control flow of the program. And then you initialize the program, and in some loop, while you decide that you need more data, you perform one step, then control returns, and then you can observe the values, the current values, and do something with them. So in terms of software architecture, this is inversion of control. Control is returned after performing a minimal amount of work, so the user is free to run this whole thing in a main loop for maximum throughput, or to run it one step at a time in interrupt style for minimum latency, or to use some buffering heuristic to have a balance of both. And sometimes you can get away with pretending that data flow and control flow are different aspects, but sometimes you cannot. So there is a need for synchronization, and you can tell by some component implementing interfaces of both worlds, both a data flow and a control flow interface. The simplest case is a component that stores a value on the heap, in a heap variable, and observing the value just reads the variable, has no effect at all, and when the corresponding step method is called, then the value is updated in a clocked fashion. So this can be used to cache a value that you want to compute once and then use many times in micro time. And if you have not just one buffer, but two, then you can have a delay register. And if you have delay and feedback, then you can have stateful components, just like you would do that in hardware. So now we can go back to the original algorithm. This is the implementation of the K-hand summation data flow network in Sig-adlib. First, we allocate 2 delay registers. Then we throw in the 4 arithmetic operations that you saw. 2 of them are used more than one time, so we better have a cache for them. And then the cycles are closed by mutation by using setters, because Java doesn't have recursive let. And finally, the whole thing is bunched up as a synchronized component with an internal firing order. So when this code returns, you have a Sig-adlib program object graph that you can run to do K-hand summation on a stream. And if you do run things right away, you get an interpreter, because every program object carries a bit of an interpreter, knows how to perform its own operational semantics. And from this, we can go to compilation. Obviously, if the interpreter is modular and extensible, the compiler has to be as well. Otherwise, it wouldn't be very useful. So for every interpreter method, there is a partner compiler method that is a bit of a code generator of Java bytecode. If you forget to implement a code generator, we can always fall back to calling back into the interpreter, because there is no environment to carry around. And the compiler traverses the whole program object graph, triggers all the code generators, inlines everything that it finds, because programs are not recursive. This cannot go wrong. And in the end, you have a Java class definition of a monolithic program as a byte array on the Java heap. There is no external storage required. This can be loaded with a standard Java class loader. Then you have a new class in your JVM, and you can instantiate an object, and once you use it quite a bit, it gets hot and compiled by the JIT compiler to machine code for the machine you're running on. Compilation is fully transparent because the interpreter and the compiled components use the same API. So you don't have to tell if the component you're interfacing with is interpreted or compiled. So user is free to compile subcomponents of a bigger program at any granularity that makes sense. And we have some help in this by another tool that we have been developing in the past years called LL-Java Live, which is a bytecode generator library for immediate use, but I don't have enough time to explain the details here. The basic idea is that Java already has the capability to create and load code on the fly. The hard part is the generation of correct bytecode that survives the verification process, and LL-Java Live helps us there. And finally, we did some benchmark experiments to see how good compilation really is. For this, we tried a slightly more complex example than K-hand summation, and that's zero-crossing detection. Zero-crossing detection is very simple as long as you're doing calculus, and it's not so simple when you're dealing with real data streams, because you have discrete time, you have discrete signals, you have IEEE floating point semantics that can get very funny, and you have initial conditions all to consider. So there's a lot of corner cases to get right. And the simplest algorithm that we've been able to come up with, or the most elegant, looks like this. The leftmost row classifies the current value, whether it's positive or negative, or unsigned. That subsumes 0 and NIN and all that stuff. And then in the second row, there are two sample and hold components that track if the signal has last been seen in the positive or in the negative half plane. And if there is an inconclusive unsigned value, the previous values are retained. In the third row, there are rising flank detectors that can tell you if the signal has just entered the positive or entered the negative half plane. So these are upwards and downward zero crossings, and if the order doesn't matter, then the final row just ORs them together. The code looks much like the previous example that you saw. First, we make a copy of the input signal. I'm going back one slide. Everywhere where there's a fan out, it's a good idea to use a cache so that you don't duplicate computations. Then there are the guard operations with some comparisons. Then we have sample and hold. We have rising flank detectors. And finally, bunch up the whole thing with a firing plan that makes sense. This uses two subcomponents, sample and hold, and rising, and I'm not going into the details, but they're not very complicated either. And then I try to run this program in 3 versions. The interpreted version right away, then the compiled version, which is obtained just by calling a method that's named compile, and finally a baseline version that has been carefully handwritten in C and compiled with GCC, with some bunch of random walk data so that there are zero crossings in interesting places. Yes, thank you. And it turns out that the interpreted version is okay-ish. It can do 5 million elements per second on a single CPU core on my machine. And the compiled version speeds up by a factor of 47, and it's just as fast as the C version. I haven't been able to measure any difference. So, to conclude, Sig-adlib is an embedded domain-specific language for data flow programming. It's mostly functional, but not quite in some important places. Because it's a dynamic language, it has no global analysis that the compiler can do for us, so we have to deal with micro-time control flow explicitly. The usual workflow is first you draw the data flow diagram, and then you do topological sorting by hand. The language integration into Java is very tight. It's a reactive inversion of control API with very little overhead, very predictable resources. The language is modular, extensible. You can come up with a new component class with an interpreter and a compiler at any time. That works because the object-oriented data abstraction is very clean here. And compilation support is completely transparent for the user. So in the end, we can have the best of both worlds. We can have rapid prototypes of programs in interpreted mode and very high performance. And finally, I do have some demo equipment with me. If you're interested in seeing and hearing Sig-adlib in action, meet me in a break and we can have some live organ music. Thank you.
All right, thank you very much. We have a few minutes for questions. Anybody? Sorry, I have low blood pressure. Oh, we have a question.
Thank you. My question is, what's the eventual use case? Or maybe in other words, like who sponsors this project?
Well, our main use case is interactive audio synthesis. Because Marcus is not only a software engineer, but also a musician by profession. And for the sponsoring, well, we wish we had more.
A great talk. So my question is, you are operating on the streams, right? So do you try to follow the reactive manifesto and reactive streams API in Java that was developed some time ago?
No.
Okay. And are there any plans for that, for example, to combine that with other streaming frameworks, basically to allow this kind of interoperability?
Yes, I'm not sure, because my impression is that the basic restriction of streams
So I'm not
is very,
the
hard.
The Java 8 streams, I mean like the akka streams, for example, and the reactive manifesto that was so they developed the API for that, and there you can implement that yourself, basically. Like akka stream is implementation of reactive stream, for example. So that was my question, like, for example, the akka or other platforms like this.
I see. Well, I haven't looked into the details. I did have a very close look at functional reactive programming and arrows, and many of the abstractions that you gain by using arrows about the nature of time and so on is actually not useful for us. It's something that we want to have explicit control over.
Yeah, I see. Thank you.
Perhaps one small remark for the first question. In musical practice, there are a lot of systems which make data processing networks like these graphic PD or Max DSP by the ILCAM Institute, and they are very widely used by musicians to produce sound and to produce reactive environments where an instrument plays together with a computer and things like this. But they are all very theoretically very unpleasing. Yeah? There is no semantics and no predictable behavior there. So we try to give an alternative where you can say what the system is really doing. Yeah? I know a very famous and very reputed composer who makes Max DSP settings for his large environments, and what he does every time he makes a concert, he starts the network and tries if it works, and if not, he reboots the computer and starts again. And this is the normal practice in this area. So that's the point where we want to find something which is a little bit more mathematically founded.
We are out of time for questions. You can always meet the speakers afterwards in the lobby. Is Damian Frolik here? So come over, and I'll take the privilege, because I'm Trackos here, to ask one more question. Since you are a musician, which instrument do you play and what genre of music? What kind of music do you play and what instrument?
I personally, I'm a classical composer, and I play a little bit piano, but the main thing I do is composing, and yeah. You can see it on my website.